Today we'll study an important concept in permutations and combinations, and that is Catalan numbers. Now a sequence of numbers 1, 1, 2, 5, 14 and 42, this is called as Catalan sequence. And these numbers C0 equals 1, C1 equals 1, C2 equals 2, C3 equals 5, C4 equals 14, C5 equals 42. They are called as Catalan numbers. Nth Catalan number Cn, it is expressed by 2n Cn upon n plus 1. So if we have to find say C4 will be 8C4 upon 5. So it will be 8, 7, 6, 5. Now this is 5 and it is 4, 3, 2 and 1. Now this 5 will cancel. 8 will cancel. Now this is 2. So this C4, it is 14. So using this formula, we can work out any nth Catalan number. Now we'll prove that any Catalan number 2n Cn upon n plus 1, it is an integer. So what we'll do is we'll write 2n Cn minus 2n Cn minus 1. Now it will be this factorial 2n upon factorial n minus factorial 2n upon factorial n minus 1 and factorial n plus 1. Now here we'll take factorial 2n, factorial n and factorial n minus 1 common. So here we'll have 1 by n minus 1 by n plus 1. So it will be this factorial 2n and this is factorial n and n plus 1, which is 2n Cn upon n plus 1, and that's your nth Catalan number. Now this left hand side, there are binomial coefficients, and this is greatest binomial coefficient 2n Cn minus 2n Cn plus 1 will always be a positive integer. So this Cn, which is 2n Cn upon n plus 1, will always be an integer. Now this Catalan sequence, it was first studied by Euler in 18th century when he was working to find out number of ways of dividing a polygon into triangles. So while solving these problems, he came across Catalan sequence. Now the sequence, it is named after mathematician Eugene Charles Catalan, who studied connection of these Catalan numbers with right use of parenthesis. And the name Catalan numbers, it is given by mathematician John Riordan. It was as late as 1988, it was discovered that it was studied by a Mongolian mathematician in 1730. So this is the earliest use of Catalan sequence in any known literature. Now these Catalan numbers, they have wide variety of applications in combinatorics. Now let us take up an example. Now suppose we consider a sequence A1, A2, A3 up to A2n of 2n terms formed by n copies of plus ones and n copies of minus ones. Now we have to find number of sequences in which no initial string of this sequence has more minus ones than plus 1. Now this number of sequence, it is given by Cn, which is your nth Catalan number. Now say for example, suppose we have 2 plus 1s and 2 minus 1s. Now we can create a sequence of these 4 numbers so that no initial sequence has more minus 1 than plus 1. They will be given by plus 1 minus 1, plus 1 minus 1 and plus 1, minus 1 and minus 1. Now we take any initial sequence, this one, this one, this one, or this one. No string has more minus 1s than plus 1s. And here also, this initial string of 1, string of 2, string of 3 and string of 4, number of minus 1s is not greater than number of plus 1s. So there are only two ways to do that, and it is equal to C2. Now if we take 3 plus 1s and 3 minus 1s, then the sequence could be plus 1 minus 1, plus 1 minus 1, plus 1 minus 1, or it could be plus 1 minus 1, plus 1 minus 1 minus 1, or it could be plus 1 minus 1 minus 1, plus 1 minus 1, or it could be plus 1 plus 1 and then minus 1 and minus 1. And we also have this plus 1 minus 1 plus 1 minus 1 and minus 1. So there will be 5 such cases. So for this one, it will be equal to C3, and that's your third Catalan number, which is 5. So each initial string, it will have either more plus 1s or at least as many plus 1s as minus 1s. Now we'll prove this result that number of such sequence, it is equal to Cn. So we need to find number of sequences formed from n copies of plus 1s and n copies of minus 1s, so that no initial sequence of string has more minus 1s than plus 1s. So we can rewrite this statement or mathematical problem as any partial sum a1, a2, a3 up to ak, it should be either greater than 0 or equal to 0 for any k from 1, 2, 3 up to 2n. So in any initial sequence, number of plus 1s should be either greater than number of minus 1s, or they should be at least equal to number of minus 1s. So now we need to find number of such sequences possible. Now we know that from n plus 1s and n minus 1s, the total number of sequences that can be formed is arrangement of these n plus 1s and n minus 1s, and it can be done in factorial 2n divided by factorial n ways. So total number of sequences that can be formed from all plus 1s and minus 1s will be given by 2n Cn. Now in 2n Cn, there will be some sequences which will follow this property. We call them as acceptable sequences. And then there will be sequences which do not follow this property, and we say suppose they are unacceptable sequences. Now this is say an and this is un. Now we need to find number of acceptable sequences, and we have to prove that number of acceptable sequences is equal to Catalan numbers. Now we'll find this an indirectly by calculating this un, which is number of unacceptable sequences. So what we'll do is we'll consider an unacceptable sequence un formed from n plus 1s and n minus 1s, and since it is unacceptable, then there must be at least one smallest k. So we'll find one smallest k which doesn't satisfy this property. So in that case, we'll have a1 plus a2 plus a3 up to ak, and it must be less than 0, and this k, it is the smallest one in this sequence. Now since this is the first unacceptable sequence, it clearly means that this ak, it must be minus 1, and this k, it must be an odd number. So if k is odd, then remaining k minus 1, they'll be even numbers, and k minus 1, they'll be k minus 1 by 2 plus 1s and k minus 1 by 2 minus 1s. So in the sequence of k numbers, we have k minus 1 plus 1s and then k plus 1 by 2 minus 1s. Now, if we look at other terms in the sequence from k plus 1, k plus 2 up to a to n, it will have n minus k minus 1 by 2 plus 1s and n minus k plus 1 by 2 minus 1s. So that's how this entire sequence will have n plus 1s and n minus 1s. Now what we'll do is we'll construct a sequence b1, b2, b3, bk, bk plus 1, bk plus 2 up to b2n, and what we'll do is these first k terms of the sequence, we'll choose them from the sequence a1, a2, a3 and ak by changing their signs. So we'll choose these first k terms as minus a1, minus a2 and minus ak, and for these remaining terms we'll choose them as ak plus 1, ak plus 2 and a2n, so without changing their signs. So it'll be ak plus 1, ak plus 2 and a2n. Now in this sequence of b, number of plus 1s will be k plus 1 by 2, and then number of plus 1s in this sequence, which is n minus k minus 1 by 2. So here k by 2 and k by 2 will cancel. We'll get this as n plus 1. And if we look at number of minus 1s, now number of minus 1s will be number of plus 1s in the previous sequence. So it will be k minus 1 by 2 plus n minus k plus 1 by 2, and it will be equal to n minus 1. So this sequence bn, it will have n plus 1 plus 1s and n minus 1 minus 1s. And in this case, if we add all the terms in the sequence, then the sum will be simply 2. Now in this proof, what we'll do is we'll prove that number of unacceptable sequence, it is same as number of sequence in which sum of numbers is 2. That is number of sequence formed from n plus 1 plus 1s and n minus 1 minus 1. So we'll prove that there is a bijection between un and the sequence, say bn. Now in this first part, we have established that for every unacceptable sequence, we can create a sequence in B such that its sum is 2. Now we'll prove its inverse. Now let us take a sequence B, which is b1, b2, b3 up to b2n, and it has n plus 1 plus 1s and n minus 1 minus 1s. Now in this sequence, we will choose a sequence in which the smallest element is k, such that this b1, b2 and bk, it has more plus 1s than minus 1s. Then we can define this function gb as minus b1, minus b2 and minus bk, and then bk plus 1 up to b2n, and this is our original sequence in un. So this is the original unacceptable sequence in un. So basically there is a bijection between the sequence of b's and unacceptable sequences. We can write number of unacceptable sequences un, it is given by number of sequences in this set B. Now in B we have n plus 1 plus 1s and n minus 1 minus 1s. Then number of sequences that can be formed is given by factorial 2n upon factorial n plus 1 factorial n minus 1. So now we have total sequence and we have un. Then from there we can write an as factorial 2n upon factorial n minus factorial 2n upon factorial n plus 1 factorial n minus 1. Now here we'll take factorial 2n upon factorial n minus 1 common. So we'll have 1 upon n minus 1 upon n plus 1. Now we simplify this, we'll get this an as 2n cn upon n plus 1, which is nothing but nth Catalan number. So total number of acceptable sequence, it is given by Cn. So if we take n plus 1s and n minus 1s, then number of sequences in which any initial sequence will have more plus 1s or at least equal number of plus 1s and minus 1s will be given by this Catalan number Cn. Another application of Catalan numbers is in Dyke's words of length 2n. Now if we have sequence of n x's and n y's, then a Dyke's word is defined as a string consisting of n x's and n y's such that no initial string has more y's than x's. So if we look at Dyke's words of length 6, that is value of n is 3. So here we have 3x and 3y, and we have to arrange them in such a way that in every initial string, number of x's should be at least equal to or more than number of y's. Now we can arrange them as x, 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 y, 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 or we can write x, y, x, x, y, y, or x, y, x, y, x, y, or x, x, y, x, y, y, or x, x, y, y, which is 5, and 5 is nothing but it is C3. So number of Dyke's word of length 2n, it is given by Cn. And it is same as this previous question. If we choose this x is plus 1 and y is minus 1, then every initial string should have more or equal plus 1s than minus 1s. So it is same problem formulation, except that instead of plus 1 and minus 1, we are choosing x and y. Now another application of Catalan numbers is in parenthesis problems. So if we have n left parenthesis and n right parenthesis, then number of expressions in which n pairs, they are correctly matched, it is given by Cn. Now say for example, suppose we have 3 left parenthesis and we have 3 right parenthesis, then we can write them as this one. Now the next one could be, or it can be, or, and finally. So there are these 5 cases in which left and right parenthesis, they are correctly matched, and this is given by C3, and C3 is 5. Now this again is a simple case of Catalan numbers. So a parenthesis is correctly matched if in any initial strings, number of left parenthesis, it should be greater than or equal to number of right parenthesis. So as long as in any initial sequence, number of left parenthesis, they are greater than or equal to number of right parenthesis, then they are correctly matched. So again, if we take left parenthesis as plus 1 and right as minus 1, it will give us this same sequence of plus 1s and minus 1, which will lead us to nth Catalan number Cn. Now another application of Catalan numbers is in Dyke's path problem. Now suppose we have Dyke's path of length 2n consisting of n northeast strokes and n southeast strokes, then number of ways of arranging these up strokes and down strokes so that it never crosses this x-axis or horizon, it is given by nth Catalan number Cn. So say for example, if we take n as 3, so we have 3 up strokes and 3 down strokes. Now we can arrange them so that they never cross x-axis in 5 ways. Now Dyke's path, it will cross x-axis only if number of downstrokes is greater than number of upstrokes in any initial string. So that means all the Dyke's path, they'll be acceptable if number of upstrokes is either greater than or equal to number of downstrokes. So if we take this as +1 and this as -1, so this problem will again give us Catalan number Cn. Now so far we have defined this Catalan number Cn as this binomial coefficient 2n Cn upon n plus 1. Another way to write Catalan numbers, and which is in terms of recurrence relation. And recurrence relation is Cn plus 1, it is equal to this summation Ck Cn minus k, where k varies from 0 to n. So any n plus 1th Catalan number, it is equal to C0 into Cn plus C1 into Cn minus 1 up to Cn into C0. So that is the recurrence relation between Catalan numbers. Now we'll prove this recurrence relation using our same initial example. So suppose now we have a sequence containing two n plus 1 numbers, say a1, a2, a3 up to a2n plus 2, containing n plus 1 plus 1s and n plus 1 minus 1s. Now we know that number of acceptable sequence, it is given by this Cn plus 1. So we already have answer to this problem, and it'll be this Cn plus 1. Now we'll prove that another way to write this Cn plus 1 is in terms of this summation. Now what we'll assume is, let 2k plus 1 be this first term in the sequence where sum of this partial sequence a1 plus a2 plus a3 up to a 2k plus 2, it is 0 for the first time. Now if we look at the sequence, which is a1, a2, a3, and this is a 2k plus 1, a 2k plus 2, and this is a 2k plus 3 up to a 2n plus 2. Sum of the sequence is 0 for the first time at this number a 2k plus 2. Now to the right of the sequence, we'll have two n minus k terms. So we'll have n minus k plus 1s and n minus k minus 1s, and number of sequences to the right of a 2k plus 2 will be simply c n minus k. Now here in this sequence, this a 2k minus 2, this has to be minus 1, and a1 it is plus 1. So we already know a1 is plus 1 and a 2k plus 2 is minus 1. Then we are left with this sequence of 2k numbers having k plus 1s and k minus 1s. Now if we choose any initial sequence from A2 such that number of plus 1 should be greater than or equal to number of minus 1s, then the sequence, if we add 1 to it, will always be greater than 0. So it can never be greater than 0. So number of sequences in which A1, A2, A3, A2k plus 1, so that none of the partial sequence is 0, will be given by acceptable arrangements of k plus 1s and k minus 1s, and which is given by Ck. So if the sequence it is 0 for the first time at 2k plus 2, then number of ways of writing the sequence is Cn into Cn minus k. Now this k, it can vary from 0 to n. So total number of acceptable sequences will be given by this summation. K varies from 0 to n, Cn, C, n minus k, and it is equal to Cn plus 1, and which is what we need to prove in this question. Now we can use this recurrence relation to associate Catalan numbers with other variety of combinatorics problems. Say for example, suppose we have a circle, and on this circle we have two endpoints. Then number of ways in which these points can be connected in pairs such that resulting line segments, they do not intersect. It is given by Cn. Now if we take n as 1, then there will be 2 points on this circle. So there is only one way. So suppose it is t1 and t1 is 1. Now if n is 2, we have 4 points. So it can be either this or this. So t2, it is 2. Now if we root one vertex, say 0, then if we choose one line like this, in that case, so here on the left, it will be 0 vertices, it will be given by t0, and here we will have 2n minus 2 points. So it will be given by tn minus 1. Now next we can choose this because we need even number of points. So here we have only one way, which is t1, and here on the right we have 2n minus 4 points. So it will be simply tn minus 2, and it will continue up to tn minus 1 into t0. So this is nothing but this is your tn. So this tn is this summation. K varies from 0 to n minus 1 tk and tn minus k, where t1 is 1 and t2 is 2. So again this is nth Catalan number, which is Cn. Now another application is polygon triangulation problem. Now if we have n plus 2 gone and we have to divide it in n triangles by drawing n minus 1 non-crossing lines between vertices of polygon, then number of ways of doing it is given by Catalan number Cn. So if we have this pentagon, so this is 5, which is n plus 2. So n in this case is 3. Now Catalan number says number of ways of triangulation of this pentagon is C3, and C3 is 5. Now we can show these 5 cases also. One of them is this way, another one is this. Then we have this one, and this one, this one. So we have 5 ways to triangulate this pentagon. Now in order to prove this, what we'll do is we'll consider this n plus 3 gone and let us say vertices are v1, v2, v3 and some vk. Now let us choose this v1, v2. Now if we choose this third vertex C, then we are left with this problem in which we have to triangulate this. Now number of ways of doing this is simply t0, and then we are left with this n gone having n plus 2 sides, and number of ways of triangulating is simply tn. Now if we choose this v4, then here we have 4 sides, then number of ways of triangulating left will be t1, and on the right will be tn minus 1, and it will continue till tn and t0. So basically triangulation of this n plus 3 gone, which is tn plus 1, it satisfies this recurrence relation tk and tn minus k, where k varies from 0 to n. Now t1 is 1, T2 is 2. So basically this is recursive Catalan sequence. So number of ways of triangulating this n plus 2 polygon will be simply Cn using this recursive relation. Now we also use this recursive relation of Catalan numbers for rooted binary tree problems. So a rooted binary tree will always start from a root, and then either it will have 0 nodes or 2 nodes. So such a tree is called as rooted binary tree. A rooted binary tree with n internal nodes and a node is internal if it has 2 branches coming out of it. So having n internal nodes is given by Cn. So if we take n as 2, then it will be this one or this one. So in this case, it will be equal to C2 and C2 is 2. And if we take n as 3, then we'll have 5 cases, which is your C3. Now, if we consider any binary tree having n plus 1 internal nodes, then we have this rooted node, and then we'll have some nodes on the left and some nodes to the right. Now, in this case, number of nodes, it is given by, say, bn plus 1, and then we'll have this one case when number of nodes in left is 0 and number of nodes in right is n. So it'll be b0 bn, or 1 here and n minus 1 here, b1 bn minus 1, and it goes all the way up to n and 0. So it'll be this bn and b0. So we can write bn plus 1 as this summation k varies from 0 to n, bk and bn minus k. Now if we look at b1, that is only one internal node. There is only one such tree. For 2, it is true. So b1 is 1, b2 is 2. So this sequence, it satisfies initial conditions and it satisfies recurrence relation of Catalan numbers. So for this n plus 1 internal nodes, number of binary trees will be simply Cn plus 1. So for rooted binary tree with n internal nodes, it can be constructed in Cn ways. There are countless use of Catalan numbers in combinatorics problems. Now it is your task to go and explore the world of Catalan numbers.